Okay. Of course I screwed up the last one, so I'm having to redo this one. But anyway, so here we go. Electric circuits. Now, here's where we start. All right. Get this little iPad thing. Isn't that modern? Aren't they hip? Aren't they hip? These slides are from 2007 now. So, that was all the rage. Okay. So needs battery pack, needs charge to move. And that's what we have. You need a battery pack for the energy, change in voltage, because you got charge in here, you got a voltage difference, Q times V, so therefore you got energy. And what a battery does, listen to me, is it takes chemical energy and converts it into electrical energy. Okay? All right? And it's called the electric motive force. All right? And that's what batteries do, is they push charge. So we've got this fancy thing called E, the EMF. You hear about the EMF, and we call it the electric motive force. What the heck? The EMF. All it is voltage. That's all it is. You know what it does? It pushes charge. That's it. It pushes charge. That's what it does. It pushes charge through that wire. Okay? And the way we calculate how it pushes that charge through the wire is this way. The electric current, and when the charges are moving due to that potential difference, the potential difference is equal to that electric field times the distance apart, between the voltages. And so boom boom. Electric field's pushing that charge through there, and we've got a current. And the current is equal to the change in charge over the change in time. And that's called an ampere. Okay, so first equation, I equals change in Q over the change in T. Okay, so now, let's say we've got a 3-volt battery in a calculator. Got a 3-volt battery, and the battery draws I is equal to 1.7 times 10 to the negative 4 amps. Okay, doesn't draw that much current. Remember, it will still hurt. It'll still hurt because 50 milliamps, a half an amp can kill you. Got to be careful. 15 amps, which has come out, because they'll say, 500 milliamps will kill you. Why do you call it 500 milliamps? Why don't you say a half an amp? Anyway, this is not near a half an amp. So calculator won't hurt you. And you'll feel a little buzz, but it won't hurt you. It's current that kills you, okay? Not voltage. Because when you walk across a carpet, you generate about 10,000 volts when you shock yourself on the door. That's about a 10,000 volt blast. The problem is there's not a whole lot of charge there, and the current's really small. So you just get a little sting, maybe, or it kind of feels funny. All right? And let's say it's on for 1 hour. So delta T is equal to 1 hour. How many electrons run through that thing? Okay, well, we'll take 1.74. How many electrons? All right, well, we'll take I is equal to 1.74 times 10 to the negative 3, 1.7 times 10 to the negative 4 amps, which is equal to that change in charge over 1 hour, 3,600 seconds. Multiply that out. Now, here's another thing I want you to do. I want you to make sure that you always do your calculations in this stuff in scientific notation like that. Times 3,600 equals 0.61, or 6.1 times, we'll just call it 0.61. 0.61 coulombs is my change in charge. So how much energy? What's the energy? Hey, you know this. Change in charge times the change in voltage, or QV, 0.61 times 3 equals about what? 1.8 joules. Now, here's the next thing I want you to think about. Okay, what's the power? Then what's the power? Of this calculator. Now, this is jumping up to but I want to tie it together because I want to be able to do the derivation here of, a conceptual derivation. In other words, so what's the power? Well, we know what power is. It's the joules per second. Don't you ever forget that. .84. So the joules here was 1.84 joules per 1 second. That's the power. But where did we get that 0.184 joules from? Right. We got that 0.184 joules from, we calculated the amount of charge, and the amount of charge was equal to the 1.74 amps per 3600. Okay, so where we got Q over S was equal to the 1.7 times 10 to the negative 4 amps. So we've got a change in charge over change in time. Okay, so we'll take that change in charge over that change in time times the voltage. Look what I've got. Charge times voltage. That's an energy. Divided by the change in time. So we've got 1.84 because when I divided this out, I got 1.74, and I figured out 1.74 times the voltage. 1.84 joules per second would be my power. In other words, power is equal to the current times the voltage. Now we'll learn about resistance. But first, let's go back and make sure we got the slides down. Okay, direct current is what we're going to deal with in most of this chapter. We look at alternating current just for a second, but alternating current shows up when we do Faraday's law after we learn a little magnetism. We're going to get all magnetic in chapter 21. We're going to learn all about magnets. In chapter 2, we're going to put it together with Faraday's law. Right? And then that's where we get an alternating current. We'll look at some of the basic calculations of it in this chapter. That's what we just did. Conventional current. All right, now here's one last thing before I move on. Conventional current is a device that shows. Now, we know that if we have a battery here, and we're going to try and get power to this, or current to this device, all right, that the electrons are going to flow this way through it. We actually look at conventional current, which is what Benjamin Franklin came up with, which I talked about today in class. He's kind of the father of electricity in a lot of ways. So we always look at as if the protons are flowing. But it doesn't matter, because we're still going to get a bunch of negative charge over here and a bunch of positive charge over here. Because we had a bunch of protons pile up over here, what's going to happen? Get a bunch of electrons are going to go, ooh, I want to be close to those protons. They're going to pile up over here. Or the protons are going to move down this, but that's not what happens. But okay? So we just use conventional current, and you'll see that it's not that big a deal. And it actually, the mathematics of everything still works out. even using that direction. All right, so now resistance. So now we're going to talk about Ohm's law, and it's so cool. Okay,